Yes, welcome. This is 300 Plus Academy, where all we do is exams, tutoring, making sure you ace your next exams, not exams, because of course, some of us we have more than two, three exams to write for the year 2024. In case you're just joining us, I can tell you that this is the right place to be. So, moving on into the interesting subject of physics, we're going to be taking off with an introductory lecture into the world of physics, looking at how we measure quantities, units, talking about fundamental and derived quantities and their respective units. We will be looking at dimensional analysis, and of course, we'll be looking at measurement, precision, and all of that. So join me as we take a dive into the world of physics. So when we say physics, what is physics? That is the first thing to start with. Physics is a subject that deals with matter and energy. As you can see on the board, you recall that the other two branches are biology and physics, where biology deals with life and living organisms. When you talk about chemistry, it deals with matter, talking about the composition, the changes that matter can undergo. And but when we talk physics, what we practically do in physics is we assemble matter. We assemble matter. We are not looking at the composition necessarily now. What we do is that we assemble matter, and then when we assemble matter, we look at what we can use that matter for. When I say usage in this case, we talk from the perspective of energy. Take for instance, if we assemble matter to make a ceiling fan or a standing fan, we must have assembled matter that way. Now, what that matter will now do is to help us convert electrical energy into the mechanical energy that rotates the fan. Look at the wireless mic I am using. Matter has been assembled in this case, but now this is now converting energy. Now it's converting electrical energy into sound energy. So you look at a moving vehicle, a car, matter has been assembled. So what happens is that we put fuel in the car. That matter will help us to convert the chemical energy from the fuel, and then convert that into mechanical energy, which moves the car. So practically, when we say physics, what physics does is that it deals with matter and energy. It's just about matter and energy interaction, and then there are various branches of physics. We talk about mechanics. At this level of physics and mechanics, we'll be dealing with motion, that's kinematics. We'll be dealing with dynamics, talking about momentum. We'll be looking at work energy and power vectors, equilibrium of forces. We'll be looking at simple harmonic motion, projectiles, uniform circular motion or curvilinear motion. We'll be looking at things like machines. We'll be looking at pressure. We'll be looking at density. We'll be looking at friction and all of that. When we talk mechanics, under thermodynamics, we'll be looking at temperature and its measurement. We'll be looking at things like calorimetry, other specific heat capacity, latent heat, thermal expansion in solid and liquid, method of heat transfer, and the likes. Electromagnetism is there, where we'll take a dive into electricity. We'll look at electric fields. We'll look at magnetism, both DC and AC. We'll look at that. Then talking about acoustic wave, we'll be looking at wave, properties of wave, sinusoidal equation. We'll be looking at relativity. We'll be looking at quantum physics, otherwise known as quantum physics, and the like. So optics is there. That's talking about light and mirror, both mirrors, lenses, and the like. So I can assure you that you're going to enjoy your preparation as you aim towards UTME physics for the coming year. Now, I repeat again here, I said physics is a physical science. In other words, it's a science that seeks to create. It's a science that seeks to innovate things so that it makes our world easier to live in. Physics is a physical science that assembles matter in most cases and consequently change energy from one form to another. It simply creates. When you look at most things around you, matter has always been assembled as far as physics is concerned. Then what the matter help does is to change or convert energy from one form to another. Take for example your pressing iron. What it just does is very simple. Matter has been assembled, and then you supply electrical energy as you put into the main switch. You supply electrical energy, which is then converted into heat energy, which you use in pressing or ironing your clothes as it were. So you find out that physics is just a physical science, and it is interesting, by the way. Now, I said yes, since it combines materials or matter, we then talk of measurement. Since we want to assemble matter here, if I want to assemble matter, I now have to begin to talk about how heavy, how light the materials I want to assemble is. For example, talking about this wireless mic now, I know how light it is, how light it feels. When you check things around you, you know how heavy or how light. So when you talk about how heavy or how light something is, it means you're talking about mass. Mass, as far as physics is concerned, is a quantity. So the things we measure in physics are what we call quantities. So since we are creating in physics, since we want to combine materials or matter together, we therefore talk about measurement of quantities. We want to measure certain quantities. If we're talking about, let's say, how bright this studio is, for example, then you're talking about a measurement, the intensity of the light. Is it dim? Is it bright? That is a measurement as far as physics is concerned. That's a quantity. So we talk about measuring quantities of what we want to create. So, and since we are going to measure quantities, those quantities must have unit. Take for instance, if I say what is the distance, what is the length, and you say 5, it could be, maybe you're telling me $5, maybe you're saying 5 meters, but the moment I hear 5 kilogram, I know you're talking mass. I know the quantity you're talking about is mass. If I hear 5 degrees Celsius, I know the quantity you're talking about is temperature. If I hear 5 Newton, I know the quantity you're talking about is force. If I hear 5 kilogram meter per second square, it is still force. If I hear 2 pascals or 2 Newton per meter square, I know you're talking about pressure in this case. So what I'm saying here is that since we are going to create in physics, therefore we must measure certain quantities of the materials we want to assemble. So since we are measuring, then we also have to talk about the units of those measurements we want to take. So talking about the things we measure in physics, that's the quantities that we measure in physics. They fall into 2 categories. The first one is fundamental quantities. Fundamental quantities meaning basic quantities. When you talk about fundamental quantities, they are quantities that you cannot define in terms of other quantities. Imagine I'm talking about length, and I'm now telling you that, imagine I'm talking about length, and I'm now telling you that length is a quantity that when I combine temperature with length with acceleration, it doesn't make sense. This length is a basic quantity. I cannot define it in terms of other quantities. I cannot use other quantities to define it. Length is just length. It is fundamental. I cannot use other quantities to define it. You can see I said fundamental quantities are quantities that cannot be defined in terms of other quantities. They are simply independent. Yes, they do not depend on other quantities. They are independent of other quantities. They are the basic or foundational quantities upon which physics stands. They are the foundational quantities upon which every other measurement, every other quantities that we are going to have in physics, they stand on the foundational quantities, and they stand on the foundational quantities, and that is fundamental quantities. So that ends that. Now, talking about our fundamental quantities, so if we have a quantity, if we have a measurement that we want to take, then that measurement must have its own unit. So talking about fundamental quantities, they are being accompanied by their own fundamental units. So if fundamental quantities are quantities that you cannot define in terms of other quantities, then fundamental units are also units that you cannot define in terms of other quantities. Take, for instance, the unit of length is meters. So if you say a fundamental unit, meter, how do you define that? So you cannot define them in terms of other units. They are simply independent of other units. So talking about fundamental quantities, there are about 7 of them. The first one is length, and the unit is meters, represented by M. The second one is mass, M. The unit is kilogram, kg. The third one is time, represented by T. The unit is seconds. The fourth one is current, I. Ampere, that's a flow of charge. The fifth one is temperature, how hot or how cold the body is. That's in Kelvin, absolute temperature there. The sixth one is amount of substance, that is mole, given the mole. Then the last one is luminous intensity, how bright light is, and that is candela, CD. Now, looking at these fundamental quantities, we still have those that are the most fundamental in these 7 fundamental quantities, and they are length, mass, and time. Length, mass, and time are the 3 most fundamental quantities, and it has been internationally agreed that meter, kilogram, and seconds, MKS system, yes, MKS system, that's the SI unit, internationally agreed system of units for length, mass, and time in physics. That's all as it is here. This is a UTME question. As you see displaying on your screen, I have a let me bring the first question here. So the way we are going to proceed as far as physics is concerned is, once we start with the lecture, we immediately start to attempt those UTME questions that relate to whatever we are discussing. So as you can see on your screen, in 1978, question 9, the first question there states that the internationally agreed system of unit SI for physical measurements are what? You have about 5 options there, and when you look at this, they said this is kilogram, meter, and seconds. Option C is the correct option there. So it has been internationally agreed. These 3 are the most fundamental of the 7 fundamental quantities. And it has been internationally agreed that their SI units should be meters, kilogram, and seconds. So in physics, if you're given quantities in grams, if you're given your mass, quantity of stuff a matter contain, if you're given in gram, you have to convert it to kilogram. If you're given your length or your distance in centimeter, you have to convert it to meter before you use it. If you're given in your timing in minutes or in hours, you have to convert to seconds, because that is the meter, kilogram, seconds system of SI unit. So that ends that on fundamental quantities. We move quickly into derived quantities. On to the second type of measurement we are taking physics, talking about derived quantities. When we talk about derived quantities, as you can see on your screen, physical quantities derived from combination of the fundamental quantities, either by product multiplication of the fundamental quantities or by quotient, that's division of the fundamental quantities or both. But once we combine the fundamental quantities, we usually will have the derived quantities. Take for instance, if I say area, area is a derived quantity. In this sense, I only have to combine. I have to look for the product of length and breadth. Product of length and breadth here gives me the derived quantity area. So when you talk about derived quantities, they are quantities that are usually dependent on the fundamental quantities. Derived quantities can be defined in terms of other quantities. That is, they can be defined in terms of the fundamental quantities. So just like fundamental quantities have fundamental units, derived quantities also have derived units. So let's take them one after the other, and then I'll talk about dimensional analysis. When we talk about area, area is given the formula. That's the derivation is length times breadth. Since our SI unit is in meters, so length and breadth here, they are all looking distance, they are all looking length. So that's meter times meter. That will give us meter square. You talk about volume. Volume is length times breadth times height. So in this case, that will be meter, 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 the product. So the unit will be meter cube. You talk about speed or velocity. Fine. Speed we know is a scalar quantity. Velocity is a vector quantity. For speed, you're looking at distance moved per unit time. But for velocity, you're looking at the displacement moved per time, or you're looking at distance moved per unit time in a specified direction. But they both bear similar, same formula, by the way. So speed or velocity, that's looking at your distance or your displacement divided by time. Distance is length, so that's in meter. Time is in seconds, so that is in meters per seconds. This is how we write that, meter per second. Of course, those of you conversant with indices, you know that this being down, this is going to be x raised to power minus 1. It will surprise you why we are taking everything from the basics like this, because we have amongst those preparing for this exam, those whose foundations are totally weak, is purely non-existent. We have people moving from the arts and humanities, from the social science class, moving into the science class. There are people in that class. We have people who are working class, who's not had access to, some of these things in time past, who are just making that switch. So that is why we have to think things as basic as possible. And remember, we said we believe in inclusiveness here at 300 plus academy. But over time, once the foundations are well laid, then we can ramp up things and, of course, meet up with the various exams that we have next year. So moving on, acceleration or retardation. Retardation or deceleration is negative acceleration, but it is still velocity over time. Velocity here is in meter per seconds. So I have seconds here. Meter per seconds. Now, seconds raised to power minus 1. Then here, it is more like I have a 1 here. So that's meter per seconds raised to power minus 1. According to the law of indices, you know that this division should become minus 1. So that is meter per seconds square. Meter per seconds square. Written this way or this way. I am coming to dimension and dimensional analysis much later. Now, talking about force. Force is product of mass and acceleration. So my mass is in kilogram. My acceleration now is in meter per second square. So if I bring this here, that is kilogram meter per second square. Now, a special name is given to kilogram meter per second square, and that is Newton, after Sir Isaac Newton anyway. So if I say kilogram meter per second square, is the same thing as the special name Newton. Talking about weight. Weight of a body is the product of mass and the acceleration due to gravity, which pulls every object back towards the center of it. So what we have here when we say weight is mass times acceleration due to gravity. Of course, acceleration due to gravity still bears the same unit as acceleration here. So what you have here is kilogram times meter per second square. and that's why you have the same unit, kilogram meter per second square or Newton. So when you talk about work is force times distance. Since my force is in kilogram meter per second square, then my distance is in meter. Now this meter here goes with this meter here. So meter times meter gives me meter square. So kilogram meter square per second square. And since so which means the unit for my work, the derived unit for my work is kilogram meter square per second square. Since force has a special name, Newton, and then this is meter, so it means if I say Newton meter, it is the same thing as saying kilogram meter square per second square. And work also has a special name given to it in terms of unit, that is joules, represented with J. Now, energy, of course, mechanical energy, there are various forms of energy, but energy is the capacity to do work. But here, talking about mechanical energy, the two, which is the one we are very much conversant with, talking about the potential energy and kinetic energy, energy due to the position of a body, and this is energy by virtue of the movement of a body. Now, potential energy is mass times acceleration due to gravity, which is a form of acceleration, times height. This mass times acceleration due to gravity was exactly what we did there, mg. So that is kilogram meter per second square times this mass. So mass times this mass is going to give me mass square. Then I have per second, so that's kilogram meter square per second square. So when I look at that, kilogram meter square per second square is just the same thing as joules, and I can invariably represent that as Newton meter as well. Half mv square, my half is a constant, so it doesn't even hold sway. Mv square, my mass is in kilogram, velocity is in meter per second. Velocity is in meter per second. So square, I have a square out here, so if this should square, so meter square, seconds raised to power minus 1. Minus 1 times 2 minus 2, so that's kilogram meter square per second square. So that is still the same thing as we had for our work here. So that is why for energy we can as well represent that in joules. Talking about density, density is mass over volume. Now in this case, mass is in kilogram, volume is in meter cube, so that is kilogram per meter cube. Of course, we can write that as kilogram per meter cube and will still be correct. Young modulus, yes, it is tensile stress over tensile strain, where stress is force over the cross-sectional area of an elastic material. Strain is the extension produced divided by the original length, the actual length. So extension and length, they are all in meters, so that's meters, strike out meter. But for stress, force over area, my force is in kilogram meter per second square. That is for my force. My force is in kilogram meter per second square. Now, since the meter square is going to be down here, if I have to multiply, that's going to be m raised to power minus 2. In other words, let's say force over area, that will be Newton per meter square. And that's exactly what you have here. Newton per meter square. Newton, force is in Newton. Area is in meter square. Force is in Newton. Area is in meter. So that's Newton per meter square. So my Newton is the same thing as kilogram meter per second square. Then I have my per meter square here. So kilogram stays. M1 plus minus 2. That's 1 minus 2. So that is why I have kilogram. 1 minus 2 is minus 1. Kilogram per meter per second square. Kilogram per meter per second square. That is the derived unit. That's the SI unit of my Young modulus, which is given as stress over strain. Coincidentally, for pressure, pressure is force per unit area. So my force is in Newton, my area is in meter square. So that is Newton per meter square, also written as Newton per meter square. So having Newton per meter square, exactly what we have here is what we're going to have here. So that's just looking at some derived units. Of course, that ends that. Now, talking about dimensional analysis, remember that under fundamental quantities, I said of all the fundamental quantities, length, mass, and time are the three most fundamental quantities. They are the units upon which most of the other units, especially units on the mechanics, depend: length, mass, time. Now, when we talk about dimensions or dimensional analysis, what dimensions or dimensional analysis does is that it shows us how whatever quantities that we are talking about is related to the three most fundamental quantities. Look at it very well. What dimension tells us is that it gives us information about how quantities of physics relates to the three most fundamental quantities of physics, and that is length, mass, length, and time, or maybe LMT, whichever way you want it: mass, length, and time. Mass, length, time, preferably. So if I take, for instance, let's say I said power. Of course, power is the energy expended per unit time. So when I'm talking about energy, what is the unit of energy? We talked about energy here. Energy is kilogram meter square per second square. Kilogram meter square per second square. And my timing here is in seconds. So what I have is kilogram meter square. Kilogram meter square. Now I have x minus 2. I have 1 here. The division becomes -1 per seconds. Energy is kilogram meter square per second square. Time is in seconds. So what I have is kilogram meter square. This is x raised to power -2 as the numerator. Then this is x raised to power 1 as the denominator. Division becomes minus, and then I have 1. So that what I have is kilogram meter square per seconds cube. So this is what I have. This is the unit for power: kilogram meter square per seconds cube. Also given the we can also say since energy is in joules and the time is in seconds, we can say joules per second, also written as joules per seconds. These are all units of power, and it's also given the special name watts. It's also given the special name watt. But then, talking about dimensional analysis, I'm talking about fundamental quantity power now. I'm talking about power as a quantity. I'm talking about power as a derived quantity now. But if I am told to get the dimension of power, what I am invariably told to do is to prove or to show how this quantity is related to the three most fundamental quantities of physics, which are mass, length, and time. So in this regard, once I get the unit this way, kilogram is mass, meter square, meter is length, ml square, seconds is time, so t raised to power -3. So this is the dimension telling me how power is related to the three most fundamental quantities of physics. So ml squared t raised to power -3, that is the dimension of power. And since we have all of our derived units here, you can as well guess, not guess, we don't get this in physics, by the way. You can as well get the dimensions of our derived quantities. Take for instance, since area is in meter square, the unit is in meter square, then what it means is that meter is length, so the dimension is what? L square. If I talk about volume, Volume, the unit is in meter cube, then the dimension is going to be in L cube because meter is length. Talking about speed, the unit is meter per second. So meter is length, seconds is time. So that is LT raised to power minus 1. That is the dimension of speed or velocity. Acceleration, the unit is in meter per second square. So meter is in length, seconds is in time. So that is LT raised to power minus 2. Force is in kilogram meter per second square. So therefore, the dimension kilogram is mass. Meter is length, seconds is time. So that is MLT raised to power minus 2. You talk about weight having the same unit as force, so the dimension will be the same. If the units are the same, then the dimensions will be the same. Talking about work, the unit for my work is kilogram meter square per second square. Kilogram is mass. Meter square is length square. Seconds raised to power minus 2, that is T raised to power minus 2, so that the dimension of work is ml square T raised to power minus 2. For energy, once you look at the derived unit, then you can as well tell us the dimension. That's the dimensional analysis. Talking about density, kilogram per meter cube. So this kilogram is in, that's mass. Meter raised to power minus 3, that is L raised to power minus 3. Young modulus, we ended up with kilogram per meter per second square. So that kilogram is mass, per meter is L raised to power minus 1, per second square, that's S raised to power minus 2, that is T raised to power minus 2. So this is the dimension of Young modulus. Talking about pressure, they have the same unit, kilogram meter per second, kilogram per meter per second square, and therefore they have the same dimension of ml raised to power minus 1 T raised to power minus 2. That is that on dimensional analysis. Dimensions provide information on how quantities relate to the most fundamental quantities of physics. As we move on, I'm still going to talk about what we can use dimensional analysis for, like checking the correctness of equations and the likes. I'm still going to talk about that, but for now, at the basic level, these are our derived quantities, and these are our derived units, and these are their corresponding dimension, trying to link the derived quantity to the fundamental quantities of physics: mass, length, time. Having talked about fundamental and derived quantities, let's quickly look at some quantities and units that are equivalent, that are the same. Now, take for instance the first one, work, energy, then movement or torque. When you talk about work is force times distance. This is in Newton meter. Okay. If you talk about energy, let's pick for example kinetic energy, half ke, half mv. Let's put kinetic energy. Let's pick kinetic energy, for example, which is half mv squared. This is a constant. Mass here is in kilogram. My velocity is in meter per second, all square. So that will be kilogram meter square per second square. Of course, if you look at Newton here, Newton is kilogram meter per second square. And then I have my meter here. Distance is in meter times meter. So meter times meter, that is kilogram meter square per second square. When you look at this, that's kilogram meter square per second square. Kilogram meter square per second square. You find out that the units are the same. If the units are the same, the dimensions will be the same. Talking about moment, and as well, when you're talking about torque, you're looking at force times perpendicular distance. When you look at your work here, is force times distance. Now you understand that you're going to arrive at, okay, this is Newton meter, and if you work it, you're going to arrive at the same unit, kilogram meter square per second square. So when you look at these three derived quantities here, work, energy, then moment or torque, you will see that they have the same unit. They have the same unit, although work and energy, they are scalar quantities. You talk about your moment, that is a vector quantity. Moving on, let's look at another quantities that are equivalent. Take for example from Newton's second law of motion. Yes. Okay, let's look. Okay, moving on, let's look at another quantities that are equivalent. Let's say momentum, for example. Momentum. Remember, momentum is a vector quantity. Momentum is a vector quantity. That is product of mass times velocity. Find mass is scalar, but the v you have here, velocity, is a vector quantity, making momentum as a quantity to be a vector quantity. So mass here is in kilogram. You know, momentum is product of mass times velocity, kilogram. Then velocity is in meter per second. Okay, now moving on, let me prove to you that impulse of a force is equivalent to this. Now you recall Newton's second law of motion, which states that the force applied, the rate of change of momentum is directly proportional to the force applied to that body. The rate of change of momentum is directly proportional to the force applied. So that tells me that F equals to mv minus u over t. So when t comes here, that becomes ft. Ft equals to change in velocity. Yes, change in velocity, which of course can be written as mv minus mu, where v is the final velocity, u is the initial velocity. So final momentum take away initial momentum, but then our t time has come here. So when you look at this, my force is in kilogram meter per second squared. Then I have t, which is seconds. So if I combine this and this, I'm going to have kilogram meter x raised to power minus 2 plus 1. So I'm going to end up with kilogram meter x raised to power minus 1, which if you look is the same thing as this. Ft here is what I call my impulse, is the impulse of a force, product of force times time. And of course, if you look at change in momentum is also used in defining your impulse. It's the same thing. So when you look at it, mv minus mv is still like your momentum. It is the same. So that is to tell you that your impulse and your momentum, they are equivalent quantities. They have the same unit as well. And if the units are the same, then it means their dimensions are going to be the same. Okay, let's quickly look at another one, talking about speed and velocity. It's talking about speed and velocity, where speed is a distance over time, and we know speed to be a scalar quantity. This is going to be in meter, this will be in seconds, so that's meter per second. When you talk about your velocity is displacement divided by time, so that is in meter per second as well. Although this velocity here is a vector quantity, but the fact remains that they have the same unit. They have the same unit. So if the units are the same, so will the dimension but the same. And Young modulus. Let's look at this. Pressure, tensile stress, and Young modulus. Talking about pressure, my pressure is force over area. My force is in kilogram meter per second squared divided by area, which is in meter square. If I combine this will be kilogram meter raised to power 1 minus 2 per second square. So I'm going to have kilogram per meter. 1 minus 2 is minus 1 per second square. So this is for my pressure. Now, when we talk about my tensile stress on an elastic material with cross-sectional area, tensile stress talks about the force I must have applied divided by the cross-sectional area. So force over area, I am bound to end up with the same unit. If I end up with the same unit, it means that the unit of my pressure and my tensile stress, they are the same. I'm talking about Young modulus. Young modulus is stress, tensile stress over tensile strain. Talking about my tensile stress, that's exactly what we've expressed here. Force over area. But talking about my strain, take for instance, if this was the initial length of this elastic material, this is the initial length. If I stretch this such that this material had now extended this far, so that from here to here looks like an extension now. So my strain is actually the extension provided here divided by the initial length, that's the original length. And since, if you look at it, E over L, this would be in meter, this would be in meter. Meter will strike out meter, so invariably I am still left with what? Force over area, which in that case I'm still left with force over area. Invariably I'm still going to end up with the same unit. So that is why we say equivalent quantities and units. So if their units are the same, so will their dimensions be the same. So that ends that. Moving on, let us quickly look at some questions that has to do with units and dimensions and all we've just talked about. Okay, the first question is 1978. Question 9. You can see that displayed on your screen. The internationally agreed system of units, that's SI for physical measurement, you can see the options there. When you look at it, that is talking about mass, length, and time. And the correct option there is C. You can see that kilogram, meter, and seconds. Okay, let's look at another question. So moving on to the next question, we have 1983 question 29. We were told of the following derived unit, the one that is not a unit of power is what? When you look at it from the mechanical perspective, power is work, or you say energy per time. Work is in joules, time is in seconds. So joules per second, of course, this is correct. So, but when I'm looking at the unit I'm having here, I know that they are trying to talk about electrical work, but talking about power is given as current times voltage, and we also know that according to Ohm's law, V equals to IR. Okay, V equals to IR. So when I look at this power here, I is in ampere. Then this is volts, ampere volts. Okay, this looks correct. Also, since V equals to IR, can we just substitute IR for V here, so that if I substitute IR for V, that's going to be I times IR. I times I, that's going to be ampere square, then ohms. Ampere square ohms. Ampere square ohms. Do we have anything like that? Okay, not there. Ampere square ohms, we don't have that. Okay, let's look at, okay, what about if we make I the subject here, I equals to V over R, and then we come here and say, okay, since P equals to IV, then for I, let me put V over R there. V over R times V. V times V, that would be what? Volts square per ohms. This looks correct. So looking at C and D, C or D is the correct answer, because the question, as you can see on your screen, states of the following derived units, the one that is not a unit of power, C is not a unit of power, because to look at all the answers we have ampere square ohms, we have ampere volt, and then we have volt square ohms. So if you look at it clearly, C and D are not units of power. So you can see that this question is on unit. It's not enough to just talk about to just discuss physics verbatim and just as though you're doing you're dealing biology. No, you really have to get to work and see how things pans out. Okay, let's move forward. Another question, as you can see on your screen, is 1985 question 1. It says, which of the following is not a fundamental SI unit? Which of them is not a fundamental unit? A, option A, you can see meter there. Meter is length, which is fundamental. Ampere there is fundamental, that is for current. Kelvin there is fundamental, that is for temperature. Second there is fundamental, that is for time. But radian there is the answer. It is not a fundamental unit, but a supplementary unit. Talking about supplement, this is 1980. That question is 1985 question 1. 1985 question 1. That is a supplementary unit. That is supplementary unit, talking about radian for plane angles and steradian for solid angle. These are supplementary units. So looking at that option, E is the correct, as radian is not a fundamental SI unit. Moving on to another question, 1986 question 4. 1986 question 4. 1986 question 4. As you can see, the explainer you say, which of the following is a derived unit? Kilogram is not a derived unit. That is a fundamental. Meter, B, is fundamental. Kelvin is fundamental. Newton is derived. That is pretty direct. D is the answer for 1986 question 4. We move on. 1987 question 1. So you can see we had in 1985. Sorry, we had in 1986. Now we have in 1987. So the topic we discussed, talking about units, dimensions, and introductory physics generally, it looks as though simple, but you are always going to have questions from there. Looking at question 10, they say, which of the following units is equivalent to kilogram meter per seconds? That is, moving on, you can see the question on your screen. That is the next question in 1987 question 1. You say, which of the following is equivalent to kilogram meter per seconds? We just have to check that out. Newton ordinarily is in Newton is kilogram meter per second square. Now what I'm having here is per second, so that means 1 over okay, I can just leave that here, per second, so that what this will then mean is kilogram meter per second square plus minus 1. So this is going to give me kilogram meter per seconds cube. That is for option A. So option A is wrong. It's not correct. Then we have this one, Newton meter seconds. Newton meter seconds. Let's check option B out. Newton meter seconds. Newton is kilogram meter per second square times meter times seconds. Okay, so what this will mean is kilogram meter times meter square x minus 2 plus 1. So we have kilogram meter square per seconds. That is not equivalent to what we are looking for. Now let's look at Newton seconds. Let's look at option C. Newton seconds. They say Newton seconds. Newton is kilogram meter per second square times seconds raised to power 1. So this is going to be kilogram meter x minus 2 plus 1. That will be kilogram meter per second. And that there is equivalent to what we have here. So option C is the correct option for 1987 question 1. Option D, since option C is correct, I don't think we need to go through option D. So that ends that option C is equivalent to kilogram meter per second. Moving on to the next question, as you can see displayed on your screen, that is 1988 question 2. Which of the following are the correct SI unit of the quantities indicated? These are sort of questions that eat up time. Talking about Newton and force, yes, this is correct. Talking about torque. Torque, although it produces a rotational effect, just like what we call a couple under moment. Moment and torque, they have virtually the same unit. So you're looking at force times perpendicular distance. So this is supposed to be Newton meter. So non-Newton per meter, this is wrong. 2 cannot be there. So if I look at this, I already know that this is wrong because it has 2 in it. This is wrong, it has 2 in it. And this is also wrong, it has 2 in it. So I know that this is correct, and then I know that watt and power, this is correct. So these are questions you don't need to waste time on. Newton and force, correct. This is wrong, you know that. This is, the moment you see that the second one is wrong, any of the options that has 2 in it, this has 2 in it, this has Roman figure 2 in it, this has Roman figure 2 in it. So I already know they are wrong. I can just simply go for this. And looking at it, 1 and 3, watt for power, Newton for force. And when you talk about momentum, momentum is product of what? Mass times velocity. This is supposed to be kilogram, this is supposed to be meter per second. So not meter per second, this is wrong. So the correct answer there is option D. 1 and 3, they have the correct units. And it says, which of the following is a fundamental unit? You can see that on your screen. Option A, Newton. Option B, watt. No. Option C, joule. All these are derived units. Second is the correct. That is the unit for time. So option D is the correct answer. That is 1990 question 2. 1990 question 2. It says, which of the following is a fundamental unit? Very direct question. Second is the time. Okay, just moving on to the next question. That is 1993 question 1. As you can see on your screen, it says, which of the following quantities has the same unit as the watt? When you talk about the watt is the unit of power, and power as its way is actually work over time. So when I look at work is force times distance over time. So when I look at the distance over time is velocity. So I can say force times velocity. When you talk about watt is the same thing as force times velocity. So when I look at this, D is the correct answer, working by this formula. Force times velocity has the same unit as power. So which means if I am saying power is the energy expended per time or work done per time, I can also say power is the product of force times velocity, and I'll be correct. Yes, moving on, the next question you'll see on your screen is 1998 question 1. Yes, 1998 question 1. Question talks about which of the physical quantity that we have in the option is the same as impulse. When you talk about impulse, recall impulse is actually change in moment. Impulse is change in momentum. And if you recall very well, when we talked about Newton's second law of motion, which states that the rate of change of momentum is dependent on the force acting on it. That is, depending on the force applied, that is what will determine the extent to which the momentum of a body changes. Of course, being that this is the final velocity, product of mass times velocity is actually momentum, but this is final velocity, so that makes this final momentum. That makes this final momentum, and u initial velocity, that makes this initial momentum. So if t comes here, that becomes ft. Ft is the quantity impulse, product of force times time is impulse, and we are going to be left with mv minus mu here, which represent our change in momentum invariably, which means momentum. So when you look at it from the options displaying on your screen, that is actually okay. That's 1998 question 1. If you look at it from the options displaying on your screen, that is actually option B. Momentum, as is the physical quantity that is the same thing as impulse. It is not energy. No, it is not surface tension. Of course, surface tension is actually force over length. Take note of that. And it is not pressure, which is force over area. So that ends that about that. So we move forward. The next question, as you see on your screen, is that the correct unit of energy density. Energy density, they call it energy density. Have you heard of that before? The correct unit, that's 2006 question 20. Yes, energy density. Energy density actually means energy over volume. Recall that normally when you say density of a given body, of the mass of a given body, normally it will be mass over volume. So in this case, we are not talking about the density of a given mass. We are talking about what? Energy density. So that is going to be energy over volume. In this case, recall that our energy, okay, we know energy is in joules, but when we say joules in actual sense, let's say mgh, let's just use this potential energy. Let's get this energy. This is mass in kilogram. G is in meter per second square, that's acceleration, and then this is in meter, so this will be kilogram. Meter times meter, meter square per second square. So what you have as your energy here is actually kilogram meter square per second square. Volume actually is like volume is length times breadth times height. That's meter, meter, meter. So that is meter cube. So when you look at it, this and this is where the actual work is going to take place. So what you're going to have is kilogram meter square minus 3 according to law of indices per second square. So what you have left is kilogram meter raised to power minus 1 per second square. If you look at the option, as you can see on your screen, that is option B. So energy density is kilogram per meter per second square. That is option B. That is the correct thing. So that is energy density. So that if it means that whenever you talk density, you must be specific. What sort of density are you talking about? Are you talking about the density of a given mass, or are you talking about energy density? So that ends that. So you can see what question looks like when it comes to quantities of physics and units. So it is not enough to just read uncontrollably in physics, but you need to know how to act, what to do when you see question. That is why we are going through this question. Okay, we move on to the next question, and that is 2008 question 2. 2008 question 2. It says force in Newton, torque in Newton per meter, current in amperes, power in watt. Which of the above are the correct SI units? Force is in Newton, torque No, torque is not correct. Then when you talk about torque, you're talking about a couple of moment, and that is usually force times the arm. In this case, the arm for a couple is actually still like distance or length. So this is Newton meter, not Newton per meter, not Newton per meter as you have in that question. No, this is wrong. So when you look at it, Roman figure 1 in that question is correct. Force is in Newton. Roman figure 3, current is in ampere. Then power is in watt. So when you look at it, the question says which of the above are the correct SI units? 1, 3, 4. And that is option D. 1, 3, 4. Option D. 1, 3, 4. Roman figure 2 is wrong. So option B is the answer. Option D, sorry. Option D, as you can see on your screen, option D is the correct answer. So that ends that. Okay, let's move on. We have another question here, 1984 question 3. It is about dimension. 1984 question 3. It is about dimensional analysis. It says for which of the following underlisted quantity is the derived unit? ml square t raised to power minus 2. Okay, we have ml squared t raised to power minus 2, as you can see on your screen. And what we have there, we have moment, work, and then acceleration. Moment, work, and then the first one, Roman figure 1, is moment. Roman figure 2 in that question, as you can see on your screen, is work, and Roman figure 3 is acceleration. So which of them has the dimension to be exactly this? ml square t raised to power minus 2. Okay, let's look at moment. When you say moment is product of force times perpendicular distance, and force is in kilogram meter per second square, whereas okay, force times perpendicular distance, okay, that is in meter. So when we look at this is going to give us kilogram meter square. Meter is length, L square t raised to power minus 2. So my kilogram is mass. So when you look at it, ml square t raised to power minus 2, this seems correct. Now let's look at work. Work is also force times distance. And in this case, it is going to mean the same thing. Since this is force times distance, this is force times distance, it's going to mean the same thing. This is also correct. When you talk about acceleration is velocity over time. Let's try to confirm that. Velocity is in meters per seconds, and then the time is in seconds. So when you look at this is meter per second square. So this is meter is length, seconds is time. No. So this here is wrong. It's not correct. So the correct answer here is 1 and 2. They are those quantities that have their dimension as exactly ml square